The topic of chapter 5 is alkanes and cycloalkanes. This is where we're going to begin our look at the structure and nomenclature of a class of molecules called hydrocarbons. So, hydrocarbons are a class of compounds that are composed entirely of carbon and hydrogen. And for alkanes, the class of hydrocarbons that we're going to look at today, the formula will always be CnH2n plus 2, meaning that if we have one carbon, we will have 2n plus 2 hydrogens, which would be 4. If we have two carbons, we would have 2n plus 2, which would be 6. So we have a formula that we can use to relate the number of carbons to the number of hydrogens. And this is a reliable pattern because alkanes will be carbons and hydrogens, so hydrocarbons, containing only single bonds. There are other classes of hydrocarbons that contain bonds other than single bonds, double bonds and triple bonds, for example. But alkanes for today, we're just going to be looking at molecules that have single bonds. In organic chemistry, we have a systematic naming system, a scheme that lets us interconvert between name and structure unambiguously. This is tremendously useful for communicating because I can give you a name, and from that name, you should be able to dissect a relatively complicated structure. And vice versa, if I'm looking at a structure, I should be able to convert it into a name, again, so I can communicate it efficiently. Generally speaking, if you see the word alk, we're talking about a carbon-hydrogen chain being the main chain. If something other than carbon-hydrogen, if there's a nitrogen in the main chain or an oxygen in the main chain, they generally don't have alk in the name. And within our hydrocarbon system, ane means we have only single bonds. So if we have a molecule with a double bond or a triple bond, we wouldn't have an ane in it, we would have something else. So that's where the term alkane comes from. We have carbon hydrogen as our primary chain, and we only have single bonds. In addition to this, we have a systematic prefix to denote the length of the longest carbon chain in our molecule. The first four, for one carbon, for two carbons, for three carbons, or for four carbons in our main chain, the prefixes are meth, eth, prop, and bute. Beyond that, for 5, 6, 7, 8, 9, 10, etc., we use the typical Greek prefixes pent, hex, hept, oct, non, and dec. So if we have an alkane, that's 5 carbons in the main chain, that would be pentane, and we could guess that the formula would be C5H12, C5H2n plus 2, 12. In addition to our systematic prefix that tells us the number of carbons in the main chain, or the length of the main carbon chain, some molecules in our alkane class are cyclic. For example, you see that this is a 5-carbon ring, so it's not really pentane, so it's a cyclic molecule, so we call it cyclopentane. We have a cyclo prefix for the cyclic versions of these things. So cyclopentane would be a 5-carbon ring, cyclohexane would be a 6-carbon ring, etc. Your book has this table of the first 20 hydrocarbons in the alkane class, plus another one with 30, that shows you the number of carbons, the condensed structure, the formula, again, CnH2n plus 2, but then also boiling point, melting point, and density, which are interesting to look at because there are very clear trends here. You'll notice that all three of these trends, boiling point, melting point, and density, increases as we increase the size of the molecule. And this should make sense. Not only is the molecular weight increasing, which should raise the boiling point and the melting point, but as we have more atoms and more bonds, we could have more interactions, meaning we have more intermolecular forces between the molecules. And more intermolecular forces, of course, means more energy required to turn a solid into a liquid to break those interactions. So that would be melting, and more energy required, more heat required to break the interactions between the molecules in the liquid state and turn them into a gas that's boiling. Density is also part of that, that the more interactions we have, the more tightly the molecules will pack. So boiling point and melting point, due to increasing molecular weight and increasing hydrophobic interactions, which we might call London dispersion forces, most of these hydrocarbons are non-polar liquids or solvents, or they're waxy solids. So methane, ethane, propane, and butane, those are actually gases. And you can tell that because their boiling point is so low. But others, pentane, hexane, heptane, octane, all the way to about, I think, maybe 16 is kerosene. These are liquids, so most of these are solvents, good non-polar solvents. Once we get to very large alkanes, these tend to turn into solids, and they're usually waxy. They're soft, they're pliable. The longest or the largest hydrocarbons are tars, like things in asphalt, things like that. All right, so let's expand on this systematic approach to naming. Again, in the previous slides, we saw that we have a way to indicate what the main chain is, that it's only carbons and hydrogens, alk, that they only contain single bonds, that's the ane, and that the number of carbons can be indicated with meth, eth, prop, but, pent, hex, hept, etc. We call this IUPAC nomenclature. IUPAC stands for International Union of Pure and Applied Chemistry. This is an international consortium who's responsible for standardizing terminology and units in chemistry around the world. Many molecules have common names. These names might be semi-systematic or maybe non-systematic altogether. For example, butane, that's a 4-carbon chain. Pentane, that's a 5-carbon chain. Those are systematic names, but other versions of these, this is isobutane, that's a semi-systematic name. This is isobentane, that's a semi-systematic name. Other molecules that you might be familiar with, like acetic acid or chloroform, those are also semi-systematic or non-systematic names. We will learn these common names with experience. The more chemistry classes you take, the more molecules you become familiar with. You'll learn these things, but don't worry about non-systematic or semi-systematic names for now. Even if the book uses them, or I might throw them in sometimes in a lecture, if they're not part of this IUPAC nomenclature, I'm not going to require you to know them. But our focus in this class, for this lecture anyway, is going to be systematic nomenclature. So let's go through the steps. How can we convert a structure into a name? The first step is to find the main chain. Now, what I mean by that is we want to look for the longest continuous chain of carbon atoms, and we're going to use this name as the root for our compound. So that's what we talked about. If we've got a 4-carbon chain as our main chain, the longest chain, that would be a butane. If we've got 6, that would be hexane. Any groups that are attached to the main chain, so groups that are not part of the main chain but are attached to it, we call them substituents because they are substituted in place of a hydrogen atom on the main chain. Now, this is also important. When there are 2 longest chains of equal length in our molecule, we're always going to pick the chain with the greater number of substituents as the main chain. For example, here's a pretty big molecule. There's lots of carbons, lots of hydrogens, but you can easily spot that they're all carbon hydrogen. That's the only thing we have. So this is an alk, and it's all single bonds. So this is an ane, so this is an alkane. So what we want to find is the longest continuous chain of carbon atoms. And if you trace out a pathway from one end of a chain to the other, the longest route that you will find here is 7. Here we have 1, 2, 3, 4, 5, 6, 7. But we can also trace out a root of 7. Again, starting from the top here, 1, 2, 3, 4, 5, 6, 7. There's no other route that you can take that gives you another chain of 7 or more than 7. You can only find shorter routes. But you'll notice that if we take the route on the left, we end up with 3 substituents. There are 3 groups that are attached to the main chain that are not part of the main chain. We've got a single carbon group over here. We've got a single carbon group over here. And we've got a 3 carbon group. Again, this group is attached to the main chain over here. If we take this path on the right, we have 4 groups. We have a single carbon group, another single carbon group, a third single carbon group, and a 2 carbon group. So the correct choice for the main carbon chain would be the one on the right. The reason that we do this, it might not be apparent now, but the reason we do this is that if you have more substituents, it means that the number of carbons in each substituent is fewer. And it turns out that it's easier to name substituents with fewer carbons. So if we have a choice of naming a 1 carbon substituent or a 2 carbon substituent versus naming a 3 carbon substituent, it's always going to be easier to name a 2 carbon than a 3 carbon substituent. So we're going to choose the pathway that gives us more substituents so that we have fewer carbons in each, and it becomes easier for us to name. So that's step 1. Find the main chain, and we're going to use that as the root. So if this is how many carbons? 1, 2, 3, 4, 5, 6, 7. The root for 7 is hept. So this is heptane. Or at least the root of this is heptane. Step 2, we're going to number the chain. We're going to number each carbon in the chain. And what we're going to do is we're going to start from the end that is nearest to a substituent. So again, we already picked our longest chain. It's going to be 7. Notice that if we count from the top, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, we get to our first substituent on carbon 3. But if we count from the bottom, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, we get to our first substituent on carbon 2. So that's what I mean by we're going to begin with the end of the chain nearest to a substituent. So we're going to number this molecule from the bottom. So this is carbon 1, this is carbon 7. In general, even if you have a substituent, let's say on the second carbon, regardless of what end you name from, you always want to pick the direction that gives you the lowest sum of the numbers. So if your option is 2, 3, 4 in one direction and 2, 4, 5 another direction or something like that, you'd always pick the lowest numbers, starting with the lowest number and choosing the rest of the chain to give you the lowest numbers. So we've determined that numbering from the top is wrong because we get to the first substituent on carbon 3. Numbering from the bottom is correct because we get to our first substituent on number 2. Then step 3 is kind of the most complicated. What we're then going to do is we're going to name the substituents as alkyl groups. This yl, Y-L, means that the group, the alkyl group, is a substituent. And then we're going to append it to the root in alphabetical order. We're going to group them by substituent type, and we're going to identify them by their position on the chain. So a 1 carbon chain, if we're going to name it as an alkyl group, a 1 carbon branch would be methyl. 1 carbon is meth, substituent means is L. 2 carbon chain, or a 2 carbon substituent, is ethyl. 2 carbons is eth, substituent is il. So we've got methyl, 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 and ethyl. Now we want to group them by substituent type, and we're going to do that by saying we have trimethyl. 3 methyls, methyl, 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 is trimethyl. And then we're going to identify them by the position on the chain. So where are our methyl groups? They are on 2. We have a methyl on carbon 2, a methyl on carbon 4, and a methyl on carbon 5. So we have 2, 4, 5 trimethyl, and we have ethyl on carbon 3. So we have 3-ethyl, 2,4,5 trimethylheptane. So I've appended these to the root. Our root is heptane, and I've appended them in alphabetical order, meaning I put ethyl first because ethyl comes before methyl in the alphabet. We're going to group them by substituent type. So we're going to say 2,4,5 trimethyl instead of 2-methyl, 4-methyl, 5-methyl. We'll just say 2,4,5 trimethyl. And we're going to identify them by position on the chain with those numbers. So the name of this molecule is 3-ethyl 2,4,5 trimethylheptane. Notice the location of the dashes and commas. You're always going to put dashes between numbers and letters, and you're always going to put commas between numbers and numbers. We'll do a practice problem like this in a few slides. Notice that if we have one carbon as our substituent, there's really only one arrangement that that carbon can have. If we have 2 carbons in a substituent, like an ethyl group, there's only one arrangement that those 2 carbons can have. If we have 3 carbons in a substituent, which we would call a propyl group, again, prop is our prefix for 3 carbons, and il means it's a substituent. There are actually 2 ways that you can have these 3 carbons arranged. I'm using these red dots to indicate the main chain. So this is a single carbon coming off the main chain, 2 carbons coming off the main chain. If we've got 3 carbons coming off the main chain, the attachment to the main chain can either occur at the first carbon in our group of 3, or it can happen on the middle carbon, the second carbon in the group of 3. We have to give this a different name because if you have a connection on the end, it's going to be a different molecule than you have a connection on the middle. So if we just have a regular 3-carbon chain with the connection at the end, we just call it propyl, or sometimes we call it N-propyl. The N stands for normal, so normal propyl. But when we have this branching, a branched chain, this is called isopropyl. This molecule or this substituent is symmetrical, right? We got a single carbon with a branch of 1 and another branch of 1. So this is a symmetrical group, which is why they use the iso prefix. Iso means symmetrical or balanced, kind of like an isosceles triangle or an isotonic solution. So 2 types of 3-carbon substituents, regular propyl and isopropyl. With 4 carbons, it turns out that there are 4 ways to have our 4 carbons arranged in our substituent. We could have 4 carbons all in a row with our connection on the first carbon. That would just be butyl. Again, our prefix for 4 is but, substituent is il, so butyl. Or again, you could call it N-butyl, just normal butyl. However, we could also have 3 carbons with a branch. That would still be a 4-carbon substituent. It's just 3 carbons plus a single carbon branch. There's 2 ways to have that arrangement. You can have the branch on the first carbon off of the group of 3, or you can have a branch off of the second carbon of the group of 3. Notice that with this branch on the second carbon, that is also that symmetrical arrangement. That arrangement looks like the isopropyl group. It's just that we've got another carbon kind of stuck in there before we have the attachment. So this is called isobutyl. The other type of arrangement here, this is called sec-butyl. And I'll say for now, this is called a secondary carbon because it has 2 carbons attached to it. So it's called a secondary carbon. I'm going to mention that in a moment. But for now, know that this is called a sec-butyl group. The other way, the 4th way that we can have a group of 4 carbons in our substituent is to have this 1 carbon with 3 single carbon branches, and that's called tert-butyl. And again, sec means secondary, tert means tertiary. Sometimes this is abbreviated as just T-butyl. So again, your book wanted to highlight here that this arrangement, isopropyl, this kind of branched arrangement, and isobutyl is that iso arrangement that we saw in isobutane when I mentioned these semi-systematic names. This was isobutane. It's got this isosymmetrical arrangement. All right, back to this, what is called degree of substitution. I mentioned a secondary carbon has 2 other carbon groups attached to it. A primary carbon is a carbon that has only 1 other carbon group attached to it. Remember, when we're talking about functional groups, R is just shorthand for a carbon-based group. So this carbon in red has 1 other carbon attached to it, so it's primary. This carbon in red has 2 other carbons attached to it, so it's secondary. And this carbon in red has 3 other carbons attached to it, so it's tertiary. Notice that when we count the number of carbons attached to it, we actually ignore the main chain. That's important because technically, if we're attached to a carbon on the main chain, this would not be considered primary, but we don't necessarily know that our attachment will be a carbon in some other molecule. It might be a nitrogen or an oxygen. So we ignore the main chain when we talk about the degree of substitution of these substituents. Notice the tertiary group with these 3 R groups. That's what we have with tert-butyl. This carbon is tertiary because it's got 1 carbon there, 1 carbon there, and 1 carbon there. Again, notice sec-butyl. This carbon is secondary. It's got 1 carbon there and 2 carbons there. The iso arrangement, the carbon connected to the main chain is primary. And in the butyl arrangement, the carbon connected to the main chain is primary. This is a little bit confusing. If you notice this, the carbon in isopropyl that's attached to the main chain is actually secondary. It's got 1 carbon there and 2 carbons there, but we don't call it sec-propyl. We call it isopropyl because it's got the iso arrangement. So whoever at one point decided what these groups are going to be called decided that iso arrangement is more important than determining the degree of substitution of the carbon connected to the main chain. So just to finish that thought, N-butyl we said has a primary connection, sec-butyl has a secondary connection, and T-butyl has a tertiary connection. We've used R as shorthand for an alkyl group, a carbon-based group. We also will use X as shorthand for a halide. We can extend this naming system to include halogens. We would just treat the halogen as any other substituent. So let's look at this molecule. Again, we're using line angle here, so hopefully you're getting comfortable with reading and interpreting line angle formula. So how many carbons are on our chain? We've got 1, 2, 3, 4, 5, 6. So that is a hexane. It's all carbons and hydrogens in the main chain, and it's 6 carbons. So it's hexane, all single bonds, ane. Our substituent is a bromine, and if we were to number this chain, we would start on the left side and make this carbon 1 so that our bromine is coming off of carbon 1, because then we'd end up with bromine on carbon number 6. So we're going to call this 1-bromohexane. Bromo meaning it's a bromine substituent. This guy is also a hexane. 1, 2, 3, 4, 5, 6 carbons. In this case, we're going to be numbering this from the left side so that we get to our chlorine on carbon 3, instead of if we would number it from the right side, it would be on carbon 4. So this is 3-chlorohexane. Again, our longest carbon chain is hexane. we've got a chlorine on carbon 3. This guy here, our root is cyclohexane. Our longest carbon chain is 6, so it's cyclohexane. We've got a methyl group. This is a methyl group coming off of our ring of 6, and a fluorine, a fluoro group coming off of our ring of 6. When we have a ring of 6, we get to choose where we start our numbering. And we're always going to choose our numbering so that we have the lowest numbers on our substituents. So we're going to make this carbon 1, and whatever numbers these other carbons are doesn't really matter. But this would be carbon 1. So we've got 1 fluoro, 1 methyl, cyclohexane. And again, I put fluoro first because F comes before M. I noted here that this would be called a primary haloalkane. Haloalkane meaning it's a halogen on an alkane. Why primary? This guy is secondary. Why secondary? This guy is tertiary. Why tertiary? Well, it's because the carbon bearing the halogen is primary. It's got one other attachment in 1 bromohexane. The green carbon is the one we're looking at. It's the one that bears the halogen, and then the red is the number of other carbons on it. So that's a primary carbon. Here, the carbon bearing our chlorine is secondary. It's got 1, 2 carbon groups on it. And here, our carbon bearing the fluorine is tertiary. It's got 1 carbon group, 2 carbon groups, 3 carbon groups. Notice that it doesn't matter that our first carbon group here and our second carbon group here are eventually attached. That doesn't matter in determining degree of substitution. We just look strictly at the number of carbons attached to any given carbon. And in this case, we're focusing on the carbon bearing the halogen. So let's go through and do a quick practice problem naming a more complicated molecule. You can pause the video and try to name this. Go back, you can look over the slides and figure out the rules and apply them in the correct way. But just go ahead and pause the video and try to solve this. Okay, hopefully you found that the longest carbon chain is 8. Here I've highlighted the longest carbon chain. We go 1, 2, 3, 4, 5, 6, 7, 8. So what is our root? Our root is octane. This molecule is some derivative of octane. What's the next step? The next step is to identify our substituents. So we're going to look at any groups that are attached to the main chain. So here they are. We have 5 substituents. What are they? We have a single carbon group, another single carbon group, another single carbon group. We have a 3 carbon group, and we have a bromine. So the 1 carbon groups, those are methyls. Our 3 carbon group is propyl, but remember it's not N-propyl. It's isopropyl. Our connection to the main chain is on the 2nd carbon of the chain, of the 3 carbon chain, not the 1st carbon. So that's an isopropyl. And then of course we've got bromo. All right, let's number the chain now. Let's figure out where our substituents are. Remember, we're going to number our main chain so that we have the lowest numbers possible on the substituents. And hopefully you got that. We start from the left. If we start from the left, we get to our 2 methyl groups on the 2nd carbon. Whereas if we were to number it on the right, from the right, we'd have carbon 1, carbon 2, carbon 3 is where we get to our 1st methyl group. So now what we're going to do is we're going to append these to the name, grouped by type, in alphabetical order. And this is going to drive you crazy. So bromo comes first. So we're going to say this is 3 bromo. Then, and this is what's going to drive you crazy, isopropyl gets alphabetized by I. The isopropyl, if it's an isopropyl or isobutyl, gets alphabetized by the I. But the other modifiers, sec and tert, do not get alphabetized. You ignore sec and tert prefixes when you're alphabetizing. But iso is not ignored. You do include that. So that might have tricked you. You might have you might have arranged it by P instead of I. That's okay. I didn't tell you that. But this is your warning. You do alphabetize by iso. You ignore sec and tert. So that we have bromine on 3, so that's 3 bromo. We have isopropyl on 4, so it's 4 isopropyl. And then we're going to group our methyls together. We're going to say this is 2, 2, 6 trimethyl. And then we're going to append that to octane. So this molecule, 3 bromo, 4 isopropyl, 2,2,6 trimethyloctane. One thing you can try, think about this. Remember I said that the naming scheme should allow us to go between name and structure unambiguously. We spent these first 16 slides going over how to go from a structure to a name. But realize that you can easily go from a name back to a structure. You actually read it backward. You'd start from octane. You draw an 8-carbon chain. Then you'd put 3 methyls, one on the 2, another one on the 2, another one on the 6. Then you put an isopropyl on the 4 and a bromine on the 3. It's really quite easy to go name to structure. It's a little bit more tricky to go structure to name, but this naming system does allow us to go back and forth. Let's look at some structures and conformations of alkanes. That word conformation, not confirmation, not like you're confirming something. These are conformations. They are conforming to something. So let's look at these. These are our tetrahedra that we would expect for an sp3 hybridized carbon. In this case, it's got 4 hydrogens on it. This is a single carbon, so it's methane. This is the ball and stick model. This is called a CPK or space filling model, just to show you the relative size of the carbons versus the hydrogens. We know that for a tetrahedral carbon, the bond angle should be 109.5. A normal carbon-hydrogen single bond is about 1.09 angstroms. An angstrom is 10 to the negative 10th meters. So those are pretty standard values. That's essentially a perfect tetrahedron. Here's ethane. This is a 2-carbon chain, all carbons and hydrogens, all single bonds. So that's ethane. They've got some slightly different numbers here. A normal carbon-carbon bond is 1.54 angstroms, a little bit longer. Notice also that our carbon-hydrogen bond is actually stretched a little bit from 1.09 to 1.10, 1.1. And notice that our bond angle is a little bit stretched. Instead of 109.5, it's 109.6. Now you're probably saying, wow, aren't we being picky? We're talking about 0.01 angstroms in terms of bond length, or 109.6 degrees instead of 109.5 degrees. I am being nitpicky here, but it's important to realize that these are not perfect tetrahedra, that structures will kind of bend and stretch and twist depending on what other groups are attached. So why 109.6? That's the easiest one to imagine. Notice that when the carbon had only hydrogens, it was 109.5. But if we replace one of those hydrogens with a methyl group, you can think of this as being a methane with a methyl substituted in place of a hydrogen. Well, the methyl group is bigger than a hydrogen. So we have a big blob of electron density over here, and that's going to repel these other groups a little bit more. So this big blob strains the molecule, I guess, relative to what we might expect in a perfect tetrahedron. An important aspect of alkanes comes from the fact that they are all single bonds. Remember that single bonds are sigma type overlap that we get from end-on-end overlap from hybrid orbitals, sp3 in this case. And anytime you have end-on-end overlap, sigma type overlap, you have a bond that is rotatable. The overlap of these two sp3 orbitals is maintained even when you rotate these groups. So here, notice that the hydrogen up top is in the plane of the board, it's a line. And this hydrogen is in the plane of the board, it's a line. This hydrogen is wedged, it's coming out at us. This guy is also coming out at us because he's a wedge. And we've got a dashed hydrogen here going away from us and a dashed hydrogen here going away from us. So notice that the wedged hydrogens are kind of lined up with one another. The lined hydrogens are kind of lined up with each other. And the dashed hydrogens are kind of lined up with one another. That's shown here. We've got all of our hydrogens kind of aligned with one another. Then what we're going to do is we're going to hold our group on the left in place, and we're going to rotate our group on the right. So now the hydrogen that's in the plane of the board is pointing in the opposite direction of the other hydrogen. This one's pointing up, this one's pointing down. You can also look at it like our hydrogen here on the left is bisecting the two on the right, and you can see that more clearly here. This single hydrogen is bisecting these guys on the right. So we've rotated these. We've rotated these groups, but the overlap is still maintained. So single bonds are rotatable. We call these conformations. There's one conformation, this conforms to one shape, and this guy conforms to another shape. They're both ethane though. And in real life, in real time, these bonds are rotating millions or trillion times a second. So they're both ethane, but we might call this eclipsed ethane or this staggered ethane, but it's both ethane and it's interconverting all the time. There's a way to visualize this. These are called Newman projections. What you do is we're going to imagine looking down a carbon-carbon bond. So we've got our ethane here, and notice that our hydrogen on the left, this guy right here, is staggering. He's kind of bisecting these hydrogen on the right. We're going to imagine looking down this molecule from the end so that we're looking down the carbon-carbon bond. The way we represent this in a Newman projection is that the front carbon is represented just as a dot or a point. It's in black here. And the back carbon is represented by a big circle in red. So we're looking down this carbon-carbon bond, and we see the front carbon as a point and the back carbon as a circle. Then we're going to show the three groups coming off of the front and back carbon, respectively, at 60 degrees from one another. So these three black hydrogens on the black carbon, if we were looking from the end, we would see one carbon going up, one carbon going to our right, coming out of the board, and one carbon at our left, one hydrogen on our left going into the board. So that's what we see. One hydrogen up, one hydrogen to our right, and one hydrogen to our left. On the back carbon, again, if we were looking down this bond, on the back carbon, we would see one hydrogen down, one hydrogen up to our right, and one hydrogen up to our left. And that's what we see. One hydrogen down, one hydrogen up to the right, and one hydrogen up to the left. And you can very clearly see in the Newman projection that the hydrogen that's going straight up here bisects the two red hydrogens on the back carbon. Now remember, we can rotate that bond. So we could hold the front carbon the same, hold our black hydrogens in the same positions in space, and rotate our back group, rotate our red group. And we could rotate it so that the hydrogens eclipse each other, so that they're all lined up. We can talk about the angle between the two groups that line up with one another. That's called a dihedral angle. I don't think I wrote this on the slide, but it's called a dihedral angle, and we use theta as our symbol for that. We could say that in this arrangement, in this conformation, our dihedral is 0. There's no angle between our matched up hydrogens. We could also look, if we imagine rotating that back to our staggered arrangement, the dihedral from a hydrogen on the front carbon and another hydrogen on the back carbon is 60 degrees now. That's kind of the maximum distance that you can get from one hydrogen on the front carbon to another hydrogen on the back carbon. So that's 60 degrees dihedral. We could have some other angle, of course. In that case, we'd be closer to one hydrogen than another hydrogen. We'd usually just pick the smallest angle to represent that. So 0 dihedral, we call that eclipsed. All the groups are eclipsing one another. A 60-degree dihedral, we call that staggered because all of our groups are staggered. If we have some other angle, something less than 60, we would call that skew. Generally speaking, though, only 2 of these are going to matter. Only the eclipsed and the staggered are going to matter. If we rotate these back and forth, or around and around in a circle, the energy of that molecule goes up and it goes down. It turns out that the staggered arrangement, where our atoms are as far away from each other as possible, is the lower energy conformation. Again, that anything that can maximize the distance between what you can think of as blobs of electron density or blobs of nuclear density, anything that can maximize their distance is going to be better. So as we rotate from 0 to 60 and then back to 0 or 120, which is also staggered here, which is also eclipsed here, 120, or 180, which is also staggered. Notice that 180 is the same arrangement, really, as 60 in this case, because whether we're talking about one pair of hydrogens or a different pair of hydrogens, they're all hydrogens at the end of the day. So we really only have 2 conformations, regardless of how we define this dihedral. Let's look at propane. In propane, instead of looking at ethane, where we had 3 hydrogens on one and 3 hydrogens on the other, in propane, we're going to change one of those hydrogens on one of our carbons into another methyl group. This blue group you can think of as being a methyl group. Now we've got propane. We can look at the dihedral of propane as we look down one of these carbon-carbon bonds. On our front carbon, we would still see, let's say, 3 hydrogens. On our back carbon, though, we'd see 2 hydrogens and a methyl group. So our Newman projection would look like this. Again, 3 hydrogens on the front carbon, 2 hydrogens, and a methyl on the back carbon. Now, as we rotate this, we actually still get the same profile as we rotate this molecule, but the energies are different because our staggered, the 60-degree interaction is between a hydrogen and a methyl, not between a hydrogen and a hydrogen. And in our eclipsed conformation, our 0-degree dihedral is between a carbon and a methyl, not a carbon and a hydrogen. So our eclipsed and our staggered arrangements should be higher in energy and higher in energy or farther in energy relative to each other. This distance from our low point, which would be the staggered form, and the high point, which would be the eclipsed form, is 13.8 kilojoules or 3.3 kcal. If we compare that to ethane, it was 12.6 or 3 kcals. So the eclipsed conformation is worse relative to the staggered because we are now eclipsing a larger group. We're throwing a larger blob of electron density in there that should be more repulsive. So forcing these groups next to each other should be less favorable. And that's what we see, higher change in energy. Let's go further. Let's go to butane. With butane, we could really look down any one of these carbon-carbon bonds, but it's most useful to look down the carbon 2, carbon 3 bond so that the front carbon has 2 hydrogens in a methyl group and the back carbon has 2 hydrogens in a methyl group. And we can still rotate these groups. So now we get a more interesting profile. We have one eclipsed arrangement where the methyls are eclipsing. But we can rotate those groups 60 degrees and then rotate them another 60 degrees, and we get a new eclipsed arrangement where the methyls are not eclipsed with each other, but they are eclipsed with the hydrogens. So we have different terms for these. When the large groups are eclipsed with each other, we call it totally eclipsed. When large groups are eclipsed with some smaller group, we just call it eclipsed. If we have 60-degree interactions between the large groups, we call it gauche. And if we have our large groups at 180 degrees from one another, which is theoretically the farthest distance that you could put them from one another, we call it anti or anti. So think about it. Which one of these should be the lowest energy? Which one of these arrangements should minimize electron density overlap as much as possible? Well, it should be the anti. We've got staggering instead of eclipsing, and our largest groups are as far away from each other as they can get. So anti should be the lowest. What would be next? Well, it still should be the staggered form. It's now going to be the gauche. What should be next? Well, if the staggered anti is the best and staggered gauche is next, then we should have the eclipsed form that still minimizes the interaction between the methyl groups. The most interaction here is between methyl and hydrogen, not methyl and methyl. So the highest form, the highest energy form, should be the totally eclipsed form of butane, where the methyls are forced to interact. So we can plot that. And you see how it looks, what the profile looks like. We can rotate, say, look at our methyl dihedrals, 0 to 60 to 120 to 180. Then we go to, say, 140 or 300, and then back to 360 or 0. The 0 is totally eclipsed, so that's the highest. Then we go to a staggered form, 60, but then we have gauche interactions, so that should be lower. Then we go back to another eclipsed form, just regular eclipsed, not totally eclipsed, so that should be higher. And then we go down to our anti as we get to 180. That should be the lowest. As we repeat that, we go back to another eclipsed. That should be higher again. Then we go further. We get back to our gauche. Here we have a gauche interaction between these two methyls. So that should be lower. And then we get back to our totally eclipsed. So that should be higher. That is the profile for butane. We should be able to figure this out for any molecule simply by counting up how many gauche or totally eclipsed interactions we have. The more totally eclipsed interactions we have, the higher the energy of the eclipsed form, and the more gauche interactions we have, the higher the energy of that staggered form. This is all, again, relative to the lowest point. These are relative energies. And the lowest point should always be the one that maximizes the distance between as many things as possible and as many large things as possible. In this case, methyls. We're going to finish with a look at rings, particularly 6-membered rings. It turns out that for cyclic structures, 5 and 6-member rings, so cyclopentane is 5, cyclohexane is 6, are the most stable form of the ring. It turns out that for rings of 4 and 3, we get something called angle strain. If you think about it, a ring of 3, the angle should be 60 degrees, and a ring of 4, the angle should be 90 degrees. But we're talking about sp3 hybridized carbons who want to be at 109.5 degrees. So once we get to 4-membered rings and 3-membered rings, in order to form the ring, we have to really strain those bond angles. We have to make them much smaller than they want to be. Those atoms are being forced to be much closer to each other than they would want to be. But around 5 and 6 carbons, we get really, really close to 109.5 degrees. And this is how you do it. Notice that a ring of 6 isn't a normal flat ring of carbons. You'll notice that this ring of carbons kind of zigzags. It kind of goes up and then down, and then up and then down, and then up. So if you look at this ring not from top down, like we might in line angle form, but side on, you would see these zigzags. We call this a chair conformation. If we take these carbons and we draw them in line angle form here, it kind of looks like this. You see, we've got one carbon up, then one carbon down, then one carbon up, and then one carbon down, and then one carbon up, etc. This picture here, somebody thought at one point it looks like a chair. So this way of visualizing a 6-membered ring is called a chair conformation. In fact, if you look down these carbon-carbon bonds, carbon here to carbon here, and carbon here to carbon here, and you draw it as a Newman projection, it would look like this. You'll notice that it's really 2 regular Newman projections that are kind of connected to one another. And you'll also notice that they are staggered. They are not eclipsed, which tells you that the conformation that this ring takes is one that maximizes the distance between all the groups coming off of the carbons. So that's called a chair conformation. But the mere fact that I'm talking about a conformation means that there should be, or there probably is, some other way that these atoms can be arranged. And there is. We call it a boat. Basically what we do is we take the carbon that's down in the cyclohexane chair conformation and we pull it up and we turn it into a boat. And it looks like this. If you look at a boat conformation as a Newman projection, you'll notice that everything is eclipsed. Furthermore, these 2 hydrogens up here, the ones that end up kind of pointing right at each other, those are called flagpole hydrogens. Imagine that this is a boat and these are like the 2 things sticking up from the boat, so we're going to call them flagpole. They actually can interact with one another. They are physically close enough in space that there's significant overlap of their electron clouds. And as a result of that, they kind of twist the boat out of being symmetrical. To avoid that overlap between the flagpole hydrogens, the boat kind of twists, and it's called a twist boat. If we look at the energy profile of this twisting, it looks like this. The chair is the lowest energy form because that's the form that puts everything staggered. As we take, let's say, carbon 1 and we pull it up, we're going to kind of try to twist this chair into a boat. And we're going to pull this carbon 1 up. So it kind of looks like carbon 4, only over on this side. So as we do that, we're going to twist our chair. It's going to go higher and higher and higher and higher in energy. And we're going to end up with what's called a half chair, which is a kind of halfway point. It's a energy maximum. We can keep pulling this carbon 1 all the way up until we get to a boat. which is another maximum, but it's actually lower in energy than a half chair. But once we reach a boat, remember that these flagpole hydrogens are going to interact, and we're going to get to a slightly lower position, which is called the twist boat. So we can get from a chair to a boat by pulling carbon 1 up so that it looks like carbon 4 on both sides. But if we take carbon 4 and we start pulling it down so it looks like carbon, so it'll eventually look like carbon 1, if we pull it down, we'll get back to a half chair, and then eventually we'll get to a different chair, right? Notice that in chair 1, carbon 1 is down and carbon 4 is up. But to get to our boat, we pulled carbon 1 up, and then we pulled carbon 4 down, and we got to a different chair. These are in fact different. They might look like mirrors, and so you might think that they are the same, but they are in fact very different. I'm going to show you how they are different. If you look at any chair conformation, you'll notice that there are really two physical positions relative to the ring that the hydrogens can be in. You have one set of hydrogens that are pointing straight up above the ring, or straight down below the ring. Those are the ones in pink here. And we call those axial hydrogens because they are aligned along the axis, the vertical axis of this ring. So there are 6 axial hydrogens, 3 that point straight up, 3 that point straight down. The other hydrogens are pointing kind of outwards around kind of the equator of the ring. Those green ones are called equatorial hydrogens. You can really clearly see it in this space filling model, that here's the ring of carbons kind of along this flat plane. There's a little bit of zigzag in there, as you can see in the ball and stick model, but it's a relatively flat ring. We've got 3 axials pointing straight up, 3 axials pointing straight down. The other 6 hydrogens are pointing outwards, kind of like around a belt around the ring. Those are equatorials. If you look from above, you see the axials pointing straight at you and the equatorials pointing outward around the ring. Can you tell, maybe you can, maybe you can't, can you tell looking at this which type of hydrogens are closer to one another and which type are farther from one another? If you can't tell, I'll just tell you that the axials are closer to each other than the equatorials are. So any group that is in an equatorial position is farther away from all the other atoms or groups than anything that's in an axial position. So here's our chair, and we've got our axials and equatorials. I'm going to flip the chair. And let's watch what happens when we flip the chair. To make this more clear, I'm going to use a methyl group as one of our substituents. Everything else around this ring is a hydrogen, but I'm going to use one methyl group. Here, I put methyl on carbon 1, and I put the methyl group axial. It's pointing straight up, and the hydrogen is equatorial. Now I'm going to convert this chair into a boat, and then I'm going to convert the boat into the other chair. So remember what we did? We pulled one of these carbons up. So I'm going to grab carbon 4, and I'm going to pull it up, and that twists us into a boat. We still got our methyl axial, but then I'm going to pull carbon 1 down to get to our other chair. And when I do that, the methyl group goes from pointing straight up to pointing outwards. Just take this whole group and just pull it down. Now the methyl is going equatorial, and the hydrogen, instead of pointing equatorial, is pointing straight down, axial. So in this chair interconversion, any group that was axial ends up equatorial. and any group that was equatorial ends up axial. The fact that equatorial groups are farther away from one another than axial groups are means that if we can put a larger group equatorial, that should minimize our energy. Looking at this picture here, you can really see that this methyl group is quite crowded when it's in the axial position. But when we do this ring flip, or this ring interconversion, the methyl group ends up equatorial, and hopefully you can see that we have a lot more room in the equatorial position. This means that one of the chair conformations is more favorable than the other. The conformation that puts the methyl group equatorial is more favorable than the one that puts the methyl group axial. We also saw that when we looked at ethane. Remember when we had eclipsing groups, it was worse. When we had staggered groups, it was better. We saw that with the rotation of ethane. We saw it with the rotation of propane. And we saw it with the rotation of butane. The same concept applies when we're looking at ring interconversions. The ring is going to spend more time in one form than the other. Remember, this is the same molecule. We're just twisting the bonds around. These are called steric effects. Steric means basically effects based on bulkiness or large groups repelling other large groups. That's called steric effects. I love this table because it shows you the effect of larger groups on the interconversion of these two forms of a cyclohexane ring. So here's a ring, and we've got some group. They used X here. X technically means halogen, so maybe don't think of this as being an X group, but some Z group, maybe some random group. And we've got interconversion between having the X group axial and the H equatorial, and having the X group equatorial and the H group axial. So here what we did to do this interconversion is we pulled this carbon with the X group, we pulled that carbon up, and we pulled the other carbon down, and we get this form of the chair. So this, we know, as long as X is greater than hydrogen in terms of bulkiness, that the equatorial position should be favored. So this back and forth interconversion, we should spend more time in the equatorial than the axial. That's why they show this arrow pointing more towards the equatorial side than the axial side. But this table shows you what the change in free energy is for that conversion. The delta G going axial to equatorial. So for fluorine, being axial is 0.8 kilojoules per mole worse than being equatorial. Same thing for the cyano group, CN. Being equatorial is 0.8 better than being axial. For chlorine, it's 2.1 kilojoules per mole, better being equatorial. For bromine, it's 2.5. For OH, it's 4.1. You see that as we get bigger and bigger groups, we favor the equatorial more than the axial. For a T-butyl group, this is T-butyl. It's a carbon with 3 methyls on it. So if X was T-butyl, it's 23 kilojoules per mole better in the equatorial position than the axial position. The interconversion from equatorial to axial would require an input of 23 kilojoules per mole. So keep this in mind. This basically tells you the relative preference for which group goes equatorial. If our choice is putting a fluorine equatorial versus putting a bromine equatorial, we're going to put the bromine equatorial. If our choice is putting bromine equatorial or OH equatorial, we're going to put the OH equatorial and force the bromine to be axial. I want you to practice drawing chairs. You'd be surprised how difficult they can be to draw, but it's a skill that all organic chemists need. Being good at drawing molecules is really, really important in organic chemistry because we represent everything by a structure. We don't use numbers in organic chemistry. Of course, I just showed you a table of numbers, but we won't be using numbers in much. We won't be using them in calculations. We won't be using equations or formula for anything. We represent, instead of using numbers, we represent everything with structure. So I want you to practice drawing chairs. There's a couple tricks to learning how to draw chairs. First, I want to point out that all that a chair is 3 sets of parallel lines. This pair of lines is parallel. This pair of lines is parallel. And this pair of lines is parallel. So when I draw these chairs, what I like to do is I like to draw the red pair first. So I draw 2 parallel lines kind of at a slanty angle like that. Then what I do is I draw a line from this point right here, and I try to bisect the other parallel line. So take a line and aim for the middle of that line, but I'm going to stop halfway through. I'm going to cut my line off maybe a little bit more than halfway to make it a little bit prettier. So draw a line aiming for the middle of the other line and stop halfway. Do the same thing over here. We're going to take this line and we're going to draw a straight line to bisect the other parallel line, and we're going to stop again a little bit more than halfway through. Then all you have to do is connect the remaining points. See that? Do that again. So parallel line, we're going to try to bisect this line. So we're going to go right, kind of aiming for the middle of this line, and we're going to stop around halfway through. And we're going to do the same thing here. We're going to try to bisect our first line, and we're going to stop halfway through. So we get there, and then we connect those last pieces. If you do it right, it kind of looks like a Budweiser logo. I always thought that was kind of funny. But there we go. Let's look at where axial and equatorials go. This is also very important. An axial group, remember, will always point straight up or straight down. And it's important to realize that when you have a vertex of this carbon, so notice that this vertex is kind of pointing up, and these vertexes down here are pointing down. So we have a vertex pointing up, pointing down, pointing up, pointing down, pointing up, and pointing down. When your vertex is pointing up, your axial goes straight up. When your vertex is pointing down, your axial goes straight down. So in this case, our axial is going to go straight up. Where our equatorial group goes is a little bit more tricky. We're always going to draw our equatorial going away from the ring, but it's always going to be parallel. By the way, I forgot to mention that doing it this way ensures that we accurately represent an sp3 tetrahedral geometry at every one of these carbons in the ring. But this arrangement, this direction for the equatorial group should always be parallel to the pair of lines that it is not connected to. So remember, we said it was 3 sets of parallel lines. This equatorial group is attached to our first set of parallel lines and our second set of parallel lines, but not the third set of parallel lines. So this equatorial group is going to be parallel to the line that it doesn't touch. So that equatorial group would go that way. If we look at a downward vertex, the axial is going to go straight down. So that's easy. Axial is always straight up or straight down. Equatorial is more tricky. The equatorial is attached to this set of parallel lines, this set there, and this set here, right there and right there. So the other pair is our first pair, this pair right here. So our equatorial should be pointing away from the ring, parallel to the pair of lines that it does not touch, right there, or that pair right here. Notice as well that if we represent this molecule in a normal line angle mode where we're using dashes and wedges to represent the three-dimensional arrangement, notice that the axial groups are, one is pointing straight up and the other is pointing straight down. So in line angle form, we might have one as a wedge and the other as a dash. And our equatorial groups, one is pointing up and to the right, the other one is pointing down and to the left. Our equatorial groups are pointing away from one another. So one should be represented as a dash and the other one should be represented as a wedge. So pay attention to the relative positions. That's what matters, is the relative positions. If one is up and its neighbor is down, they should be wedge and dash. Axial does not necessarily mean wedge and wedge. I will show you in a moment that sometimes it does. For example, I'll show you real quick here before I draw it. If this axial is pointing up on this carbon, notice that it would also be pointing up on this carbon over here. This vertex is pointing kind of upwards. So our axial group would go straight up. We would have axial up and axial up. So that would be, say, wedge and wedge. But in this case, one axial is up and the other axial is down. So that would be wedge and dash. It's the relative positions that matter, and I want you to practice interconverting between a chair and a line angle structure, or vice versa, from a line angle structure to a chair. So let's try an example where we convert a line angle structure into a chair. So what I've drawn for you here is a cyclohexane with two methyl groups on it. If you wanted to name this, you would call it 1,2-dimethyl cyclohexane. The cyclohexane with methyls on the 1 and the 2 carbons. So let's begin by first drawing our chair. Remember, this is something I wanted you to practice. So we'll start by, we're going to draw our first set of parallel lines, kind of at an angle like that. We're going to then draw a set of parallel lines that bisects the original. Then we're going to connect our ends with another set of parallel lines. There we go. All right. One thing that might be useful at this point is to number your carbons in your line angle structure and also number them correspondingly on your chair. Now, because this is a ring, it doesn't really matter where you start, but let's just start by making carbon 1 at the top, then carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. And we'll do the same thing on the chair. It doesn't really matter where you start. Any one of these carbons could be called carbon 1. It just means that that carbon would get the methyl group and its neighbor, carbon 2, would get the methyl group. I always like to start on this carbon right here. That's my favorite carbon to start. So I'll make that carbon 1. And then since we're going clockwise from carbon 1 to carbon 2 to carbon 3 in our line angle structure, let's also go clockwise from carbon 1 to carbon 2 to carbon 3, etc. in our chair. There you go. So what we need to do is we need to decide whether these methyl groups are going to be axial or equatorial. Now, it doesn't really matter where you start, because once we flip the chair, anything that started as axial would end up equatorial, and anything that started equatorial would end up axial. But we need to figure out if this is going to be one axial to equatorial, or one equatorial to axial, or both equatorial or both axial, so that when we flip it, we end up with the right relative structure. So the way I like to look at this is that on carbon 1, the methyl is dashed, meaning that it's going down or away from us if we're looking at the ring from the top. So on carbon 1, we have two options, right? We have the axial position and the equatorial position. Well, what do those positions look like? Remember that for carbon 1, the axial should be going straight up because it's a positively angling vertex. So we're going to put the axial group straight up, whatever that might be. And then the equatorial group needs to go parallel to the set of lines that it's not touching, which means that it needs to go that way. There's our equatorial group. So those are our only two options as to where the methyl goes on carbon 1. And since we're looking at this ring from the top down, that means that a dashed methyl group means that it's going away from us. So we can make our methyl group down, right? If our only choices are axial up and equatorial is down, then for carbon 1, our methyl group should be equatorial. Now, what's axial? What goes axial there? Well, there's a hydrogen. I didn't draw it, but remember that in line angle structure, any bonds that are not drawn but should be there, carbon needs a fourth bond, that should be a hydrogen. So that hydrogen is coming up. It's going up. So that means that it needs to be in the axial position. There we go. Okay. Now looking at carbon 2. Let's do the same thing. On carbon 2, we get one axial and one equatorial. But where does the equatorial go and where does the axial go? Since carbon 2 is a downward pointing vertex, that means that the axial group needs to go down. And the equatorial group needs to go parallel away from the ring, parallel to the set of lines that it's not touching. So it needs to go right there. So that's our axial down and our equatorial up. Looking at our line angle structure, our methyl is going up. So our only choice here is axial down, equatorial up. So our methyl group would go equatorial. And again, we still have one more bond that's unaccounted for on carbon 2. Since the methyl is going up, there should be a hydrogen that's going down. So that's our hydrogen that's axial. We can put him axial down here. So that is one of our two chairs. Notice that, again, like I mentioned earlier, that even though one methyl is dashed and the other one is wedged, they both end up equatorial in this case. So don't associate equatorial with being dashed and axial with being wedged or something like that. You need to figure it out each time you draw a molecule. All right, so this is one version of our chair, but remember that whenever a chair flips, we get a new conformation. And I'll set it off to the side for a moment so that we have it as a reference. Now what we're going to do is we're going to flip the chair. So when we flip the chair, actually, I'll bring it back here. Remember the procedure. We were going to grab one of the end carbons, if you can think of it that way, and pull it up or down. And then we're going to grab the other end carbon and we're going to pull it down or up. So in this case, what we could do is we could take carbon 1 and we're going to pull it down. And we're going to grab carbon 4 and we're going to pull it up. So what we get for that ends up being the same. Again, it's still a 6-membered ring. It's still a chair, but everything is in the opposite position. So instead of starting with our set of parallel lines leaning that way, say left to right, we're going to draw it backwards. We're going to have our initial set of lines leaning the other direction. Now, I always have more trouble drawing the chairs this way than the first way we did it. For some reason, say a left-handed chair is easier for me than a right-handed chair. But you follow the same set of procedures, a pair of parallel lines. We're going to bisect them. with their original, like that. And then we can connect the ends. There you go. So let's, again, keep track of where our carbons ended up. Remember, this is now carbon 1. We pulled it down, and we're going clockwise around the ring from carbon 1 to carbon 2 to carbon 3. So that's going to be carbon 1, this is going to be carbon 2, that's going to be carbon 3. And remember, we pulled carbon 4, which was down here on the left. That was carbon 4. We pulled it up. So there's carbon 4. Now all we have to do is go back and place in our equatorial and axial groups. But remember that anything that was axial in the first chair ends up equatorial in the second chair. And everything that was equatorial in the first chair ends up as axial in the second chair. So let's do carbon 1 first. Carbon 1 is a downward facing vertex. So our axial group should go straight down. And our equatorial group should go parallel to the pair of lines that it's not touching. So it should go out like that. Now, previously in carbon 1, our methyl was equatorial. And that carbon 1 was kind of pointing up. So our equatorial methyl is pointing outwards. When we tilt that carbon down, it's going to be pointing downward. So anything that was axial goes equatorial. In this case, it was equatorial. So it's going to go axial. So we have a methyl group there. And then anything that was axial before is now equatorial. So our hydrogen is there. Let's move on to carbon 2. On carbon 2, it's an upward facing vertex. So we can make our axial group go straight up. And then our equatorial group, this is always a little hard to draw. It ends up getting a little bit crammed, but it needs to go parallel to the set of lines that it's not touching. So it needs to kind of go that way. So in our first chair, our methyl on carbon 2 was equatorial. It now needs to be axial. And when we had our hydrogen axial in the first chair, it needs to be equatorial in the second chair. So those are our two chairs. And there should be an equilibrium between these two. These two forms interconvert. They're the same structure, different conformations. So which one is more stable? Which one should be in a more sterically pleasing arrangement? Remember that since equatorial groups are farther away from each other, by putting the bulkier groups there, we give them more room. So in this case, our choices are having two methyl groups equatorial on the left or two methyl groups axial on the right. So our structure on the left should be better. Our chair will spend more time in that form. Let's do one more example. This one's going to be a little bit more complicated, but hopefully it won't be too much more difficult. So here's another line angle structure of a cyclohexane ring. We have three substituents on it. We have a methyl group, we have a hydroxy group, an OH, which is an alcohol, and we have a bromine, a halogen. And what we're going to do, again, we're going to draw one of the forms of the chair first, and then we're going to flip it, and we're going to decide which version of that chair is more favorable. So to start, we'll draw our chair. We'll start with our initial pair of lines like that. We'll bisect like that. And then we'll connect our ends like that. Again, we can number our chair carbons and map them onto our cyclohexane carbons. So we'll make the methyl 1. That would be carbon 2 then. We can make the OH group 3 and the bromine 4. this isn't the numbering scheme that we would use if we were naming the molecule. We would order the numbers differently. We'd start with the bromine and go counterclockwise if we were going to name this. So I'm just using these numbers to help us identify which carbon is which. And again, I like to start making this carbon carbon 1, and then we'll go clockwise like we do in the line angle structure. That'll be carbon 2. That'll be carbon 3. That'll be carbon 4. And now we need to place in our axial and equatorial groups. So for a upward pointing vertex, our axial goes straight up, and our equatorial goes outwards like that. Looking at our line angle structure, our methyl group is a wedge, meaning if we're looking top down at our line angle structure, the methyl group is coming up at us. So looking at the ring from the side, like we do in the chair, our methyl group should be pointing up. So that's our methyl, and our other one is just a hydrogen. Okay, now there's nothing on carbon 2, so we can skip carbon 2. Well, there are 2 hydrogens there actually, but they don't matter. Moving on to carbon 3, it's also a upward pointing vertex like carbon 1 is. So our axial group should go straight up, something like that. And our equatorial group needs to go parallel to the pair of lines that it's not touching, which would be like that. There's our equatorial for carbon 3. So on carbon 3, notice that axial is pointing up and equatorial is pointing down. And on carbon 3, our OH is wedged. It's coming up at us. So our OH group should go in the axial position. And we'll have an equatorial group be our hydrogen. And then carbon 4 is a downward pointing vertex. So our axial group needs to go straight down. Like that. Our equatorial group needs to go parallel to the pair of lines it's not touching. So it should go something like that, outwards. Now in this case, our bromine is up, but now the equatorial group is the group that's up. Our 2 choices are axial down or equatorial up. So our bromine is actually going to go equatorial now. And our hydrogen should go down in the axial. So again, in our line angle structure, all 3 are wedges. But when we transcribe that into a chair, 2 of the wedges are actually in the axial position. The other wedge is in the equatorial position. But notice that they're all pointing up. In the chair, the methyl is up, the OH is up, and the bromine is up. And that is what we see in the line angle structure. They're all wedges. They're all coming out at us. So there's our first chair. Let's flip it now. We're going to draw our chair in the opposite direction, if you will. We're going to flip everything. So we can actually draw in, I'll draw those arrows again so we can help keep track. We're going to pull carbon 1 down, and we're going to pull carbon 4 up. And we're going to represent that by drawing our slanted lines leaning the opposite direction of the way we originally did. So we'll do that. We're going to bisect those lines like that, and then connect the ends. There we go. And now let's again map our carbons so that we keep track of where everything goes. Carbon 1 was up there, but we pulled it down. So it ends up there. That's carbon 1. And then we just go clockwise around the chair from 1 to 2 to 3 to 4. So 1 was down on the bottom right, then 2 would be next to it there, 3 would be next to it there, and 4 would be next to it there. Let's place in our groups now. Carbon 1 is a downward facing vertex. So its axial group goes straight down, and the equatorial group, hopefully you're starting to see this now, needs to go out that way. Now, in our original chair, our methyl was axial on carbon 1. So in our new chair, our methyl needs to be equatorial in carbon 1, and our hydrogen will be axial. Okay, we skipped carbon 2. There's nothing on that is of any importance. Carbon 3 is, again, now a downward facing vertex. So we need to have our axial straight down, and our equatorial would kind of go out like that. We maybe make it a little bit more angled. It's got to be parallel to the pair of lines it doesn't touch, so something like that. So in our original chair, our OH group was axial. When we flip the chair, it needs to be equatorial. So our OH group goes in the equatorial, and our H goes in the axial. And then carbon 4 is now an upward facing vertex. So our axial needs to go straight up. And our equatorial would kind of go out like that. In our original chair, bromine was equatorial. It was up but equatorial. Now it needs to be axial. When we flip, everything changes positions. And our H will be equatorial. I want to point out something very important here. In our line angle structure, everything is wedges. Everything is up. In our first chair, everything is still up. Methyl is up, OH is up, bromine is up. It just so happens that the methyl and the OH are up in the axial position and the bromine is up in the equatorial position. In our new chair, everything is still up. Only now the methyl and the OH are up in the equatorial positions and the bromine is up in the axial position. So when we flip the chair, we're really not flipping wedges into dashes. Everything that was up in the original picture remains up after we flip the chair. Okay, be very careful not to confuse that. Now, it might be difficult to interpret this based on intuition as to which chair is better than the other. In one, let's say in our first chair, we've got 2 axial and 1 equatorial. And in our second chair, we've got 2 equatorial and 1 axial. So your initial intuition might be that the one with the 2 groups equatorial is better than the one with only 1 group equatorial. And that's usually going to be the right case. But you have to consider that what if the one group that's equatorial is super, super, super big and bulky, and the other 2 that are axial are really, really tiny? In that case, it might actually be the case that the chair with 1 giant group equatorial and 2 tiny groups axial is better than the one with those 2 tiny groups equatorial and the 1 big bulky group axial. So we actually know how to keep track of this. Remember, I gave you this slide that had a table that told us what the preference is for each group being equatorial versus axial. So what we're going to do is we're going to use these numbers as kind of a scorecard. We're going to apply these numbers to our chair, and if they are equatorial, we're going to say give it a positive value. We're going to say this is a positive score for us. It's a good score for us. And if it's axial, we're going to give it a negative score. It's going to be bad. So watch how this works. We'll go back to our drawing. Let's look at our methyl groups first. According to our slide, a methyl group is more happy in the equatorial position by 7.6 kilojoules. So since in our first structure, our methyl is axial, that's bad. That's a negative 7.6 score. That's bad. How about OH? Our OH was 4.1 better in equatorial than it was in the axial. So in our first structure, our OH was axial. So that's bad. That's negative 4.1. Our bromine is more happy in the equatorial by 2.5. So this guy is in the right position, but he only gives us a score of 2.5. So if we add these up, what do we get? We get negative 9.2, negative 7.6 plus negative 4.1 plus positive 2.5. We get negative 9.2, which means that overall, this chair is unhappy. It's got the bulkier groups, the groups that are more forcefully trying to be equatorial, the methyl and the OH, are actually axial. It's hard to say. So we can go back and apply these same numbers to our second chair, but you'll notice that the numbers are going to be the same. It's just going to be the sign that's going to be different. So now our methyl is positive 7.6. He's in the right place. He's happy that he's equatorial. He's happy by 7.6 units of energy. Our OH, also equatorial, also happy, so he's 4.1. Our bromine is unhappy, but he only penalizes us by negative 2.5. So if we add these up, of course, we're going to get positive 9.2. So that clarifies what we might not have known before. Now, you might have guessed it, again, that 2 equatorials was better than 1, but that's only true if your 2 equatorials are bigger, kind of as a sum of each other, than the other axial is. So be careful of that. Don't jump to conclusions. If you're not sure, check the numbers. So that's all for lecture 5. The workshop chapters in the Stromanis book are chapter 6, part A and B. And if you'd like to use the Stromanis book for additional practice problems, I'd recommend doing exercises from chapter 7 to study for the exam.